All right, College Trade, we're at 9.5, rotation of conics. So far we've talked about conics of the form here, where we have x squared terms, y squared terms, linear terms for x, linear terms for y, and some constant. Notice we have no b term here. That b term is going to come into play when we have an xy term there. So notice none of the conics that we've dealt with before with a parabola, ellipse, or hyperbola have dealt with this term that has an xy. You can't complete a square if you have an xy term. So this is how we're going to end up dealing with it. This is a review just kind of as the book's taking how to identify the previous equations. Realize if AC, a parabola, if either one of those is 0, then you have a parabola because if you multiply A times C, you'll get 0. If you take the AC and you multiply them together and they're greater than 0, you know it's an ellipse. In other words, the signs are the same for A and C. If the signs are the same for AC, positive and a positive, they multiply, they're an ellipse. If it's a negative and a negative, multiply together to be positive, it's greater than 0, it's an ellipse. Hyperbola, again, we've talked about it before with it being a positive and a negative. Well, that's going to be a negative answer. That's going to be less than 0, or you could have a negative and a positive. All right, so now we're going to deal with what if we have a b value. So a b value is going to happen here when we're rotating about the axis. So let's say, for instance, we have some ellipse here. Well, no longer are we going to have an ellipse like this, but we're going to go ahead and have an ellipse that is going to be rotated. And we're going to have ellipses such as that. Most of ours are just going to be focused about the origin there as well. So that's what we're doing with this, is rotating these. So what we're going to end up doing is we're using this idea here where we have an alpha and a theta here. So what we're going to do is generate some equations to relate this new axis. This new axis we're just going to call x prime, y prime, meaning it's the axis that the angle has been rotated through. So looking at this triangle here, if you look at this triangle here, okay, where this is our alpha, we can go ahead and see, well, this is our radius r, okay, and then we have cosine of alpha, because cosine deals with our adjacent side and our radius, so we get our x prime value there, and then we get our y prime value there, very similar to our polar coordinates, thinking signs with our y. The other equations are coming from this triangle here, where our angle is alpha plus theta, and we can see that our x, the true x, is r times the cosine of alpha, because cosine is x, and y is r sine of theta plus x. So we'll use these to convert back and forth between our two number systems, our x prime number system, which is our axis here in the black, and our x prime y prime, which is our axis system here in the blue. So in order to get some more meaningful equations, we gotta break this down a little bit more. You don't have to know this or write this down necessarily, just notice we're adding two angles. So from our previous formula sheet, we're going to use our sum of two angles formulas here. And cosine, remember, it was cosine, negative, change the sign here, and then it was sine. And we added those alphas there, and we simplify it, and we get to this. And, well, we know what our cosine of theta is. Well, that's x prime. We know what our sine theta is. That's y prime. Okay. Same similar idea is going to come into play for this one. But what you guys need to make sure you have on your notes that you have access to in class is this stuff here. And we'll make sure to use that in class here. So what we're going to understand here is now we're going to be dealing with forms where we have this b term, okay, where we can't complete the square and get those nice equations that we had before. And we're going to rotate these conics through an angle. So we're going to see that we're going to really make use of these formulas that we had on our previous slide here. So what we're going to have is this theorem. This theorem has like a 2-page proof in our book. Go ahead and follow along with that if you want. We're just going to take it as a truth right now. So we have cotangent of 2 theta equals a minus c over b. And by doing this substitution, we hope to eliminate this term x and y and have something that we are more familiar with graphing here with conics. So notice that this a term is coming from my x, the c term is coming from my y, and my b term is coming from my xy term. All right, some things to remember about cotangent. Since we're dealing with cotangent of 2 theta, always choose the acute angle. Don't ever choose the obtuse angle with dealing with that. If cotangent of 2 theta comes out as something on our unit circle, 30, 60, 95, 45, 45, 90, it's going to be easy. And that's going to be what you're going to see on your test. But realize that what if cotangent of 2 theta comes out as 0? Well, remember, if it comes out as 0, okay, we'll talk about how to do that, and we also have to talk about what if cotangent of 2 theta comes out as a number not on our triangle, and we'll have to talk about how we deal with that. So if 2 theta comes out as 0, remember cotangent is cosine over sine, so that means we have that if it's equal to 0, it's 0 over 1. So that means cosine of 2 theta is 0, and sine of theta is 1. When does that happen? Well, it's at 90 degrees. But it's not just 90 degrees because we're saying, well, 2 theta is 90 degrees. So that actually means that our theta is going to be 45 degrees. So that's if our cotangent is equal to 0. 2 theta is equal to 0. The other thing we have to talk about is if it's not on our triangles, we have to inverse it. But we got to remember with our principal angles, with our inverses, cotangent, we don't have that inverse button on our calculator. And tangent's inverse, you get positives in quadrant 1 and negatives in quadrant 4. But with cotangents, you got to remember that cotangents, principal angles, are positive in quadrant 1 and negative in quadrant 2. So for that, we're going to say, let's go with cosine, because we know that cosine ends up dealing with the same principal angles, that the principal angles for cosine are positive in quadrants 1 and negative in quadrant 2. So, and then at the end, don't forget to divide by 2, or you can use the half angle formula to go backwards there. So let's go ahead and do an example here. So we're going to discuss the equation. So we want to be able to find certain points here for 2x squared plus square root of 3xy plus y squared minus 10 equals 0. Notice our b term here is the square root of 3. This is our a term, our b term, and our c term. So our c term, really, we have a 1 there. Okay, so as we plug that into the equation, we get 2 minus 1 over the square root of 3. So we have cotangent of 2 theta is equal to 1 over the square root of 3. Or we can say the tangent of 2 theta equals square root of 3 over 1. Well, where does that happen? Well, that happens when our angle is equal, or 2 theta is equal to 60 degrees. Well, we divide that by 2, and now we have our theta of 30 degrees. So that's step number 1 to get our angle. Next, what we're going to do is we're going to plug them into these formulas that we made sure we wrote down previously. So we're going to convert now and rotate our axes and have a x prime, y primed axes. So in order to do so, we take our angle, plug it in for our thetas. Well, cosine of 30 degrees is square root of 3 over 2. Sine of 30 degrees is 1/2. And then Same thing over here. Sine is 1/2. Cosine is square root of 3 over 2. Notice our cosines switch sides here, and sine switch sides, and our sines are different there for our x and y. So now that we know what x is equal to and what y is equal to in our new coordinate system, we're going to go ahead and plug that in to our next equation. So for this, I'm going to go ahead and pause it and catch you on part 2.